So with that, I think we should get going. So welcome everybody to the January LOF&BE webinar. My name is Sarah McAllister. I'm co-hosting these with Sam Manzello and Sayaka Suzuki. Just to let everybody know, we'll do questions. If we've got some pressing ones, we'll do them after each of our speakers today, right? Because we've got 3 student speakers today. And we'll do questions via the chat box. So yeah, without further ado, I will introduce our first speaker today is Jacques De Beer. He is currently a PhD student in the Department of Mechanical Engineering at the University of Maryland in College Park. He's working on ignition quantifications of decking materials exposed to firebrand attack, which is what he's going to be talking about today. I think I'll just keep it brief and let you get at it there, Jacques. Go right ahead.
Perfect. Thanks, Sarah, for the introduction. Yeah, hi, everyone. My name is Jacques De Beer. And as Sarah mentioned, I'll be talking about the thermal characterization and ignition study of Western red cedar when exposed to firebrands. So when we look at the research motivation for wildland urban interface fires, typically in the media, we see these huge flames, thousands of acres burned. But one thing that's not very accurately captured is the socioeconomic impacts of these wildland fires, with structure losses being one of them. And in the US, there's this compelling statistic that structure loss rate is on the rise, with more than 80% of structures lost within the last 6 years in California. So there's an urgent need to design structures in wildfire-prone communities that can withstand and survive wildfire events. So when we think about wildland fire, urban interface fire exposure conditions, they typically characterize them into 3 distinct categories, being direct flame contact, radiation, or in my case, which I'll be focusing on, firebrands. Post-fire studies also indicate that the ignition of structures due to firebrand exposure has significantly contributed to fire spread within the WUI. So what are firebrands? They are typically hard particles in the order of a few millimeters, liberated from the combustion of vegetation or structural components, and they have the potential to ignite fields ahead of the fire front. There are 3 processes used to describe their behavior, typically generation, transport, and I'll be focusing on the ignition. And then materials that have been used for decks have also been identified as being susceptible to firebrand attack. So when we consider a few previous firebrand ignition studies that have looked at both singular firebrands and firebrand piles, these post-fire investigations have found that firebrands tend to accumulate in groups. Manzello and Associates has also led a very successful campaign looking at the ignition of common materials when they goes to firebrands, looking at everything from airflow, firebrand pile, loading size, and structural configuration. 2 researchers at the University of Maryland also looked at quantifying the transient heat fluxes from firebrand piles, noting that both the increasing the firebrand pile coverage density and the airflow velocity increases our peak heat flux to the surface on which it's exposed. But one thing that a lot of these studies lack is that most firebrand ignition studies do not couple the ignition behavior of a material with the thermal exposure effects of the pile. So the goal of our project was to design a bench scale experimental protocol to study the ignition phenomena of firebrand piles deposited on WUI materials, to quantify the ignition of event parameters like burn time, ignition propensity, to resolve the firebrand pile thermal exposure when deposited onto a material, using gas analyzer measurements to identify burning behaviors, to quantify the relationship between the ignition propensity and airflow or firebrand pile size, and to elucidate the role of firebrand piles in the ignition of common WUI materials, considering all these measurements. So as I mentioned, we developed the bench scale wind tunnel, and it can be separated into 3 main sections: a contraction cone, a test section, and an exhaust. When we consider the contraction cone, this is where our fresh inlet, this is the inlet for our fresh oxidizer, which is moved through a reducer. And it then also comes with a honeycomb mesh, which straightens and laminarizes the flow before it's pushed into the test section. So when we consider the test section, this is where the sample is mounted along the bottom interior wall of the test section. The bottom face of the sample is exposed, allowing for back surface temperature measurements using a FLIR E95 IR camera, with a gold mirror also being used to redirect the view of the camera to the back surface of the material. And then optical access to the top and side surface of the material is gained via borosilicate glass cutouts, with the ignition events recorded using 2 DSLR cameras. And in the exhaust, we have a high temperature suction fan with a fan adjuster to control the airflow, and a 72-hole gas sampling probe, which is installed in such a way that it opposes the direction of the flow and is connected to a non-dispersive infrared gas analyzer used to measure volumetric carbon dioxide and carbon monoxide concentrations. So just a quick overview of how we run these experiments. The material substrate is placed within the tunnel, the airflow velocity is set, and the firebrands are prepared. The gas analyzer data logging system is used. The video and fluor IR recordings are also initiated. And then, as I mentioned, we make use of back surface temperature measurements. Just to show here, we deposit our fibrants on the top surface of the material. The back surface is coated with a no emissivity, high temperature black coating. And that's how we actually measure our temperatures. And then the glowing fibrants are deposited onto the sample material. The tunnel is then sealed, and the experiments proceed until all fibrants are consumed. So the material substrates that we considered, we looked at two different substrates, one being K-wool PM insulation board. This material was selected as it was used to adequately resolve the heat exposure from the fibrant pile. It was also relatively thin, having a fast response and having a thermal characteristic time on the order of about 27 seconds. The material is also non-combustible and allows us to isolate the fibrant pile thermal exposure and burning dynamics. And the back surface temperature measurements were used as a surrogate to quantify the exposure from the fibrant pile. And then we also made use of our second material, which is Western red cedar, a combustible softwood, which is frequently used to construct decks, and it was also used as its thermal properties were pretty similar to that of the insulation board. When we move on to our test matrix, we considered two different fibrant pile coverage densities. A single layer, which is or a smaller fibrant pile, which was representative of a single layer fibrant, and then a larger fibrant pile indicative of an increased hazard. As I mentioned, the material surrogates were K-wool and Western red cedar with the back surface coated with a high temperature non-emissivity paint. And we also made use of 4 airflow velocities in the range of 0.9 to 2.7 meters per second. We conducted 9 tests for each condition, equating to a total of 108 tests. So when we look at the ignition problem for Western red cedar when it's exposed to fibrant piles, we separated it into 3 distinct categories: the ignition event quantification, fibrant pile thermal analysis, and gas analyzer burning dynamics to more accurately quantify and understand the process. So when we look at our ignition events, 2 distinct ignition events were considered: the fibrant pile ignition or the ignition of the Western red cedar surface. The fibrant pile ignition is indicative of a flame located on top of the pile and typically blue in color. And it did not spread further than the pile or result in any noticeable burning dynamic changes. And we thus concluded that it doesn't pose any increased hazard. But in the case of the Western red cedar surface ignition, we noticed that it's more likely to lead to fire growth due to direct engagement of the flammable substrate. And it is indicative of the presence of a diffusion flame, typically amber in color, attached to the surface of the board. And the flame extends along the length of the Western red cedar board, preheating the Western red cedar surface. So when we consider the flaming ignition location, we noted that the majority of the ignitions occurred within or in front of the leading edge of the fibrant pile. And this is as a result of the front of the pile being directly exposed to the airflow, which promotes smoldering of the board and increased fibrant pile temperature. And the surface in front of the pile, free of fibrants, is also directly exposed to the thermal insult from the pile. Okay. When we now look at the surface ignition probabilities, we noticed that by increasing your fibrant pile coverage density from the smaller to the larger pile, we saw a drastic increase in the ignition probability. And then looking at the increased or the larger fibrant pile mass, we noticed that it was affected by changing the airflow velocity. And as the airflow velocity increased, we saw an increase in the ignition probability up to a critical point where after any further increase in the airflow velocity resulted in a decrease in our ignition probability. If we also look at the ignition time, we note that there is a decrease in the ignition time with an increase in airflow, and then there's again a rapid increase of any further increase in the airflow. This rapid decrease is attributed to the increased fibrant pile oxidation rate to the surface of the board. And then as we reach this critical point and we increase our airflow, convective cooling and dilution of the Western red cedar pyrrolizate starts to affect our ignition times. Again, this is a qualitative trend where we see a decrease or an increase in a decrease. When we move on to the thermal analysis of a fibrant pile, as I mentioned, we used K-wool as the material surrogate. We separated the fibrant pile deposition area into 3 distinct zones: a leading zone and a middle zone, which is underneath the pile, and a pre-leading zone, which was the zone in which we saw most of our surface ignition. It was noted that the location of the peak back surface temperature continuously shifted during the test from the leading portion to the back portion of the pile. When we consider some average thermal profiles for our K-wool fibrant pile thermal analysis, this is just a representative case for a larger pile at 2.4 meters per second. We note that both the leading and pre-leading edge increases and then rapidly decreases, while our middle zone actually increases and holds steady for quite a long period of time. It should also be noted that in the time frame where we note our peak back surface temperatures, this is also the time frame where we note most of our ignition events. So moving on to the peak back surface temperatures, the fibrant pile smoldering intensified as the airflow increased. This is for our larger pile mass. And then at elevated airflow velocities, a cooling effect starts to affect the thermal exposure from the pile to the sample surface. This behavior of an increase until we reach a certain airflow velocity and a decrease is also representative of what we saw for our ignition probability, where at elevated airflow velocities, there's actually a decrease in the ignition probability of our board. And then finally, we consider our gas analyzer burning dynamics. The gas analyzer measurements comprise volumetric percentages of carbon dioxide and carbon monoxide, and they were used to elucidate the burning dynamics of the fibrant pile in Western Red Cedar. The heat release rate is typically a parameter used to describe the intensity of burning, and was calculated considering the energy coefficients for carbon dioxide and carbon monoxide and our mass flow measurements of both CO and CO2. The second parameter we considered was the modified combustion efficiency, and it can be used to identify the presence of smoldering or flaming, with literature indicating smoldering in the region of 0.6 to 0.85. Initially, only the deposition of firebrands onto the inert cable was considered to isolate the combustion associated with our glowing firebrands. So when we consider the firebrand pile burning dynamics, when we consider the heat release rate, directly after depositing the firebrands, the heat release rate rapidly increases, followed by gradual decay. And we also noted that the region of peak heat release rate is in the same region in which we see our ignitions. Moving on to the modified combustion efficiency, for all our different testing conditions, we noted that the modified combustion efficiency actually held pretty steady, allowing for us to calculate a time averaged MCE for all our testing conditions, which ranged from 0.71 to 0.88, typically in the range of our smoldering ignition. The firebrand pile ignition events, however, did not register on either of these piles. We identified earlier that this ignition event doesn't pose any hazard, and the MCE results actually show that. So moving on to taking our cable to Western Red Cedar gas analyzer measurements, the firebrand pile Western Red Cedar system burning dynamics was considered, assuming that changing the substrate would not alter the burning dynamics of the firebrands, and the Western Red Cedar contribution was isolated by subtracting the system transient carbon dioxide and carbon monoxide volumetric percentages from the cable fibrant pile profile. So on the left-hand side, we see our cable profile on the order of like 300 kilovolts per square meter. It's normalized also by the deposition area of the firebrands. And then we take our combined system of fibrant piles and Western Red Cedar, we subtract out our cable from our left, and then we get the our figure on our right, indicating an average profile with the uncertainty or the variation of our carbon dioxide and carbon monoxide volumetric profiles. The uncertainty is pretty large because we were actually able to pick up or detect the flaming ignition events on the surface using our gas analyzer profiles. And then lastly, the MCE for our Western Red Cedar. The fibrant pile Western Red Cedar system modified combustion efficiency was considered. It wasn't separated. The Western Red Cedar board initially assists in the process of sustaining a firebrand or surface ignition flame, as seen by an increase in our MCE within the region where we see ignitions. And then the MCE starts to gradually decrease as a result of the formation of char, which starts to smolder, resulting in the smoldering dominating the combustion process. So in conclusion, a bench scale experimental protocol was developed to study the ignition vulnerability of Western Red Cedar when exposed to glowing firebrands. The Western Red Cedar surface ignitions were considered more likely to contribute to fire growth. Our fibrant pile heat release rate was order of magnitudes larger than our Western Red Cedar heat release rate, which is dominated by smoldering. Ignitions occur in the front or at the leading edge of the fibrant pile. This is a very interesting discovery. The radiant exposure from the fibrant pile drives the piloted ignition process of the Western Red Cedar in front of the pile, as noted in our diagram. And the fibrant pile radiant exposure is also affected by the fibrant pile coverage density and airflow velocity. And then at elevated airflow velocities, convective cooling starts to contribute to the heat transfer process. So just some recent work that we're busy with, we're actually testing OSB as a decking material. We're testing the effect of airflow variations during a test, thus emulating wind gusts during a wildfire. And then I'm also developing a pyrolysis model for Western Red Cedar, which can be used to predict the decking material ignition events in actual wildland fire events. And with that, thank you. And this is my contact information if you have any other questions.
Thank you, Jacques. That was a great presentation. Really interesting idea, the way that you set up the experiments to look at the backside temperature, which is actually one of the questions one of the participants had was maybe to expand a little bit more on exactly how you were able to get the backside surface measurement. He was, didn't quite understand how you could get the backside temperature if it's covered by the firebrand piles. So maybe you could go back to your diagram.
Yeah, I can try and elaborate on that. So what we do is, I'll just go back to this diagram. Yeah, it's just, we'll use this as an example. So we coat the back surface temperature with a known emissivity black optical coating, which we've actually also validated using thermocouple measurements under a radiant heater coil at a known heat flux. So we quantify our emissivity, and we also note that the emissivity doesn't change with temperature over the range that we're expecting at the back surface. And then we just literally position our FLIR IR camera onto the gold mirror with a quantified reflectance, and we then capture the back surface temperature of the firebrand piles, as we see in this image. Oh yeah, here, if that answers the question. So it's all about quantifying the emissivity of the back surface. And obviously we have it as a peak back surface temperature, and I'm actually working on inversely analyzing it to get the front surface temperature, because obviously there's some sort of temperature delay between the front and back surface on which the fibrands are actually deposited.
Right. Cool. I'm assuming your gold mirror is just some kind of gold-plated surface, right?
Exactly. Yeah, exactly.
Yeah, that sounds extensive otherwise. There was another question in the chat box is how were you able to make sure you had enough mixing for your gas system?
That's a good question. And obviously, typically in cone colorimetry experiments, correct me if I'm wrong, but I think it's like 6 diameters downstream of the actual material. And obviously, we were confined because this whole experiment is positioned within a fume hood. So we only had so much space to work with. But we did actually validate our gas analyzer measurements using known composition gases. So we took a bottle of carbon dioxide and carbon monoxide with a known composition, and we would take measurements and validate it was about a distance of about a foot away from our suction fan, if we would get the same measurements as what we're actually purging into our test section. And we validated, I think, within a very close variation. I can't give the exact value right now, I can't remember. But we did actually validate all that stuff to ensure that our mixing within our test section or downstream of that is actually was enough to ensure that we had a well-mixed system. And obviously the turbulence of the fan also increases the mixing of the entire test section.
Yeah, good deal. We don't have any other questions in the chat box, but I have a really quick one because I was intrigued by the pictures that you showed of the ignition events happening and how when the ignition happened in the firebrand pile, it looked to be more often a blue flame. Was that always the case, regardless of the airflow and the pile size, or?
Yeah, so typically when we deposit the fibrands and we seal the tunnel, we actually see this flame originate, and depending on the airflow and the fibrant pile coverage density, it depends on how long it sustains there. But in most cases, for the larger pile, we would see this formation of a blue flame on the pile. And then obviously we saw the second ignition event where the actual surface of the board starts to engage.
Right. So why do you think it's blue? It's interesting.
That's a good question. We've been speculating about it. Obviously, we could do more measurements, but it might be potentially that. I think when carbon, I'm going off a whim here, but if I understand it correctly, carbon monoxide, when it burns, it typically burns blue. And Quinteri has a paper like that, but I'm speaking under correction. That's just a hypothesis.
Sounds reasonable to me. Well, barring further questions, I think, thank you, Jacques. We'll move to Nima if he wants to get started sharing his screen. Nima, I'm going to try, Masoudvaziri is a PhD candidate in the Department of Civil and Structural and Environmental Engineering at the University of Buffalo. So if he's ready, I'll let him take it away.
Thank you very much. Well, hello everyone, and thank you again for joining us I'm going to talk about part of my PhD research on the risk assessment of wildland urban interface communities for wildfires. So my research on wildfires began shortly after the Tubbs fire incident. At the time, it became the most destructive wildfire in recorded history of California, and it devastated part of the city of Santa Rosa. I'm a civil engineer, so it's always about condition of structures of different kinds and well-being of people living in these clusters of structures that we call communities. So the research questions were, what's the likelihood of such a destruction in a weak community? You know, how could this happen? And looking at the structure, what's the likelihood of that structure being destroyed or damaged to a certain level? And as we started diving into this field and going through available information, we realized that there is limited modeling capacity for fire spread in WUI areas, which we would have deeply needed to answer these questions. To emphasize the seriousness of the situation that we have in WUI communities, I'd like to mention a statistic here. One of the very first documents that I came across at the beginning of my research journey was this famous table of the top 20 most destructive wildfires in California by CAL FIRE. It basically ranks the wildfires based on the number of destroyed structures in an incident. According to that table, at the end of 2017, only 8 incidents had occurred after 2010, 5 of which had occurred in the 2017 fire season itself. Last time I checked, just a few days ago, this number is 15, meaning that 7 more incidents hit this list over the last 5 years. So 15 out of top 20 wildfire-related destructions in California have happened over the last 10, 11 years. So recent years have been an alarm on this important problem that WUI communities are facing. We also had a Marshall Fire close to Denver less than 2 weeks ago, which became the most destructive wildfire of Colorado, albeit it wasn't that large compared to what we usually think of extreme wildfire cases. To evaluate the risk associated with wildfires for a WUI community, we need to be able to estimate the probability of the hazard. In this case, probability of fire having a certain rate of spread or burning intensity, for example. Then we also need to be able to estimate if our community of interest is going to be exposed to that fire. And if so, what's the response of our community to that particular fire? Like, how vulnerable is it? How many structures are going to get affected, and how fast would that be? Well, there are many contributing variables here. We have tons of playing factors in wildland in the first place. And then we have communities with buildings of different sizes and construction materials, various layouts and vegetation, or whether there are mitigation plans in place or not, and so on. And all of these factors come with uncertainties. And on top of this, most of these factors are entangled together, and there are some dynamics going on between various subsets of these variables. So we also need to take those into account as much as possible. Now, there is a key difference between wildfire and other hazards. When an earthquake, for example, hit an area, all structures are hit by the same hazard, and their fate kind of depends on their own response and strength. But wildfire is a progressive phenomenon. So when a building catches on fire, not only we lose that building, but more importantly, it becomes part of the hazard itself. Structures burn for a longer time compared to vegetation and also release more heat. And because of this important behavior, when we try to understand what would happen in a community exposed to a wildfire, we cannot separate wildfire from the community. So we cannot think only about like one structure. We cannot think only about the community. We cannot think only about the wildfire, but we must consider the wildfire and the community at the same time in the same context. So in addition to the features we already consider for wildfires, we need to take into account the features specific to the community, like the layout, the relative distance of buildings, their characteristics, their surrounding vegetation, things like that. So to this end, we have developed the streamlined WUI fire tracing model, what we call SWIFT. It has a spatial resolution of 10 meters and temporal resolution of 5 minutes. It considers structures as distinct fuel. So in SWIFT, we have 3 fuel models: vegetation, structure, and non-combustibles like ponds or roads, like what we see here at the right side of the slide. So this is Fountain Grove community in Santa Rosa. You can see the placement of structures and the layout of the community. SWIFT has 2 of the main mechanisms of spread implemented, fire spotting and radiation, and it also tracks the source of ignition in each building. One of the important features of SWIFT is its fast execution. So it takes just a few minutes to run a case depending on the domain size and the duration of fire. The model was applied on 2 case studies, which we believe represent different levels of hazard. This is a simulation of Fountain Grove community where the TOPS fire burned down almost all the structures. We can see the jumps in ignitions due to fire spotting. Having the SWIFT provides us with the opportunity to conduct a stochastic analysis. The model includes different modules, each of which has some variables involved. In this version of SWIFT, we consider firebrands to be similar with the same weight. Therefore, we can work with number of firebrands. Wind speed is significantly influential on different stages of fire spotting, as we know, and we tried to include those effects as much as we could. We also leveraged some of the experimental findings in the literature for ignition criteria due to firebrand. One important assumption is that we assume ignition of structures by firebrands occur due to accumulation of particles on narrow stripes at the edges of rooftops. SWIFT also has radiation implemented, and it tracks the heat received by each building, and there will be ignition if a certain threshold is reached. Based on the available data, or in the simplest form, assuming uniform distributions, we conducted a stochastic analysis varying these parameters in the color orange randomly. Okay, now that we have a fire spread model for community, and it has the capacity of a stochastic simulations, we can go back to the big picture and find a way to assess the risk of WUI communities for wildfires. As I stated earlier, we need to estimate the probability of hazard and the probability of what would happen in the community in response to that hazard. So technically, at the moment, we are thinking of a sequence of 2 spread models, one for wildland and one for community. This way, we can run a set of stochastic simulations in wildland and estimate the corresponding probabilities. And then we bring in those fires and run a set of stochastic simulations for each of them using the community model. This procedure gives us the ability to evaluate the loss by conditioning certain levels of outcomes, like damages, to the certain levels of hazard. Hopefully soon enough, the research community will reach to a modeling capacity where we can have details of both parts, outside and inside of the community, implemented in one platform. But until that time, this I think is the way to approach the problem. To showcase how the result of this procedure would look like, we conducted the stochastic analysis of the community for one wildfire, only one. This is the case of a TOPS fire for the Fountain Grove community. And in this case, we define the loss in the simplest way, a binary of whether a building ignites or not. Ideally, with more detailed data, we should be able to define multiple levels of damages in future versions, which is one of the research questions that we have. The plots that we see here are the results of 2,000 simulations, and they give us quite interesting insights on the response of Fountain Grove community for a fire like to a fire like TOPS. First of all, we can read these plots by asking the question, what's the probability of having X number of ignited structures or less at a given time? So for example, after 1 hour, that is the color green, the probability of having up to 100 ignited structures is about 0.75. Furthermore, we can see that for the duration of fire, it's almost certain to have at least 80 ignitions, and there is about 25% chance for all the structures to burn. Please note that these numbers are all based on having a fire hazard as extreme as TOPS fire. Another insight that we acquire is the susceptibility of the community to firebrands. We can see in the second plot that earlier in the simulation, it's fire spotting that causes ignitions. And then when we have fires across the community, the neighboring structures get ignited by radiation in the third plot. We also have this ability to simply zoom in and track the status of individual structures and see when and how a particular one ignites. So now, if we had run stochastic simulations for wildfire spread around Fountain Grove and estimated the likelihood of TOPS fire to happen, we could condition these probabilities we see here on the probability of having a fire such as TOPS. So again, this is just a showcase of how we could assess the risk for a community. It's just a simple ignition or not, and more advanced version of this methodology could define certain levels of damage quantitatively and easily track the status of structures based on those levels and estimate the loss with the corresponding probabilities. So in this particular research that I presented, we discussed the probability framework for risk assessment of violent urban interface communities on a stochastic simulation, based on stochastic simulations. I believe since we have new findings, more data of new kinds like geodata and available computational resources these days, we need to somehow rethink how we model the fundamentals and our understanding of this phenomenon. And that's what we have tried to do here. Essentially, I think the new models will be semi-empirical, mixing fundamental physics and available data. But we are in 2022, so our simulations shouldn't be necessarily based on the semi-empirical models developed like 50 years ago. We should be able to update them now. In this new modeling process for WUI areas, we need to include features of the communities as we did here. And for now, at the moment, there is a trade-off between accuracy and runtime, the computational cost. So we shouldn't aim for only one of them. We need to have this trade-off in mind if we want to have a functioning practical platform. There are also some open questions in this research for us. For example, where is the domain of the community? Like, what would be the boundary that we consider a community? Or how wide of a region should we consider to assess the wildfire hazard for that community? Or how should we characterize the wildfire and structures so that the two models can communicate with each other? This is an ongoing work with important unanswered questions and further details to be implemented. But that's actually what motivates us to continue this work. Thank you very much for listening to me. I'd be happy to discuss further details either today or anytime later.
Thank you, Nima. That was great. I completely agree that we need a model that actually works as the wildfire spreads into a community, right? Because you said all of our wildfire models stop at the edge and we have to make a whole lot of assumptions about what happens next. So this is a great framework with which to work with. There are two questions in the chat box. One is asking whether you are familiar with the work that NIST is doing in collaboration with CAL FIRE. The contact at NIST is Alex Maranghetti's, and I've got a link for you. So I don't know if you are familiar with that or not. If you are, well, speak up and discuss that a little.
I've read about that, but not in details. So it would be great if I can have that link.
Yes,
or we can have further discussions.
Yeah, make sure to send that link to you as well.
Awesome.
There was another question in the chat box. It said, is it impressive presentation? So the question is related to figure 2 in slide 9, the probability of ignition of structures by spotting. The question is there any idea of the distance between these houses and the fire front when they start to ignite?
Houses and the fire front. So the way we implemented the transportation of firebrands is actually followed by previous studies. So we consider the wind direction and wind speed, and then we have two profile of distribution for particles, one perpendicular to the wind direction, which is a normal distribution, and then there is a profile along the wind direction, which is log normal, and the parameters depend on the wind speed. Here in Swift, we do not specifically simulate the fire itself. So here we don't kind of have that concept of fire front. We have all the cells, either vegetation structures, but non-combustibles do not burn, so I don't talk about those, but either vegetation or structures, they can burn independently. And that's why we kind of have this general idea of fire front. So in this, so here, we can see that, for example, we have these ignited structures further down the fire, although the fire starts at the edge of the community. So by fire front, I assume you are thinking of an idea like this, but then we have jumps, we have the progress of the fire as well. And this is how we are looking at it. So we don't have that line of fire. We don't talk about, I mean, we do not capture that. What we are trying to capture is what happens to each of the individual cells in the model.
Gotcha. Another question popped up here asking, in the modeling of inter-building fire spread, are you also including the effects of landscaping and ancillary structures and fencing?
That's an absolutely great question. So at this point, because of the limited inputs that we work with, we only have one fuel model representing structures. So basically, if we have a structure, it's going to be represented the same way as any other structures that we have. Okay. But with further details, we can implement these details into the model as well. So at this point, it's just a structure, one type, no further details.
I got you. Yeah, so I had a related question about whether or not you could see the effect of changing the construction of the house, instead of making it, wood siding with wood shingle roofs versus a stucco home, but it sounds like, yeah, not quite yet. Need more data. Exactly. Oosh, we have a couple more questions that have already popped up. Maybe we'll answer one really quick and then we'll save some time at the end to circle back. So you have another one here. So you showed that the drastic increase in damaging fires in California in the past 10 years, because your model relies on empirical data, i.e. backward looking, how do you account for changing fire hazard conditions over time for predicting risk modeling?
That's a really great point, actually. This is one of the things that, the points that I mentioned, we need to consider in our new modeling paradigm, the way we think about modeling fire hazard. So obviously, at some point, behind the scenes in each model, we need to fit to available data. And we see that that's changing. If we get a better understanding on the trend, or what's the underlying reasons for this changing behavior that we see, then we can also implement those in the models. So basically, with more data, to be implemented, and to consider more trends, not just some fixed values, we hopefully can improve our modeling capacity.
That makes sense. So in the interest of time, we should switch to our final speaker, Savannah, if you want to start sharing your screen. So Savannah Wessies recently completed her doctoral degree at University of Texas at Austin, and she was recently awarded a NIST NRC postdoc research associateship and will be beginning at NIST here very shortly. So with that, if you're ready to go, Savannah, go for it. I don't hear you. Are you muted? Wonder if we lost her.
Okay.
There you are.
Can you hear me now?
Yes.
Sorry, I couldn't find the unmute.
No worries.
With my screen shared. Okay, so I'm going to share my screen again.
Great.
Okay.
Perfect.
So sorry about all that. I'm glad we got it figured out. So I recently just graduated, and so this presentation is going to kind of highlight some of the work I did on firebrand ignition and heat transfer characterization over my time at UT, and I will try to keep it brief and within the 15-minute time period. So this is, again, just a highlight of that. So I'll be talking about some key parameters that we found that affect ignition, some heat transfer characterization, and fuel bed ignition signatures. Our previous presenters did a really great job of kind of going over the motivation of why people want to study wildfires. So I'll just briefly go through this. But looking specifically at the US here, we've seen over the past few years that there have been thousands of structures that have burned down, and many of them are residences. So the ignition of a home is really important to people's livelihoods and something really people in their day-to-day lives worry about. So here we're going to be looking specifically at how wildland fires transition to homes through firebrand contact. So in large-scale fires, firebrand spotting plays a major role. And here we can just see a picture of some spot fires jumping a natural break in fuel. And then it's estimated that more than 50% of structure ignitions in wildland urban interface fires are due to firebrand deposition. So these lofted firebrands can ignite homes in a variety of different methods, such as debris-laden gutters, flammable roofs, or penetration into attic vents, for example. But we still are looking at what are the mechanisms involved in that ignition due to the firebrand, due to firebrand deposition. So my research more specifically, the questions I wanted to answer in my research in grad school were, what are the hazards associated with firebrand deposition in the WUI? And then what threats do firebrands pose to structures in the WUI? And then a little more specifically, like more points that you can actually focus on were like, what physical phenomenon affect the ignition of attic insulation materials? And then what mechanisms affect the heat transfer between a hot body and a substrate? And then what methods can be used to determine if if ignition has occurred in a fuel bed? So looking at my first set of experiments here, I did firebrand deposition experiments to look at the key parameters affecting ignition. So if we're just looking at a firebrand deposited on a substrate, if we can see this energy balance here. We see the firebrands reacting or interacting with the substrate and the environment. So we'll need a meaningful coupling between the brand properties and to the ignition characteristics of the substrate. And we'll want to look at the radiation, convective, and conduction, and then also the reaction within the firebrand. So a simple experimental setup was designed. So here we have a furnace where our firebrands were generated. And they were either a single large firebrand or 5 smaller firebrands in a pile that were the same initial mass as the single large firebrand. And they're placed in a furnace and they were allowed to heat up in the furnace to auto ignition and then allowed to flame out within the furnace before they were placed as a glowing red firebrand onto the substrate material that was inside of an airflow chamber that had an impinging jet flow. And the firebrand was allowed to burn out within the furnace so that any ignition events and flames we saw within the test chamber were from the substrate and not the firebrand. And the 7 different attic insulation materials were tested, and there were 3 different airflow conditions, natural convection and 2 induced flow cases. So these are the experimental observations. So flaming was observed in the cellulosic attic insulation materials for the induced flow cases. Flaming ignition or ignition events were never observed for the natural convection cases. And then the cellulosic materials are at the top, which were denim, non-flame retarded denim, cellulose, and non-flame retarded cellulose. And then flash flaming, which was just brief flames that quickly went out, were observed in the polyurethane and the 2 polystyrene insulation materials. And we saw that for the cases where there was flaming, the time to ignition decreased with increasing airflow, and the fragmented firebrand piles generally had faster times to ignition than a single large firebrand for the same airflow and material. And so from this, we saw that the firebrand configuration, so whether it's a large or fragmented firebrand, and the airflow conditions were the key factors in substrate ignition. So we wanted to find a simple model that could provide recommendations on the propensity of an attic insulation material to ignite. So first we wanted to predict the firebrand temperature evolution. So here we're looking at the energy balance on a firebrand. And in the top equation, we can see that we're balancing the smoldering source term from the firebrand with its convective and radiative losses. And then the bottom is just that we modeled the radiation as a 2-surface enclosure. And then the pile of firebrands was modeled as a hemisphere. And then we also needed to look at the ignition model. So this is for the substrate. So we balanced the radiation from the firebrand into the specimen with the sample pyrolysis and the conduction into the sample. So at early times, the radiation conduction balance resulted in low specimen temperatures, but then there was an increase in specimen temperature with time. And then the terms highlighted in red would be material specific to the substrate material, and we would need to parameterize them somehow. So we use TGA experiments and cone calorimetry, which just for the sake of time, I'm not presenting those specific results for each experiment or for each material. So this is the results of our, our ignition model. So on the right-hand side, we can see the temperature of the firebrand, which is the red line at the top, the hotter line, and then the substrate temperature is the blue line. And then below is the mass flux based on the substrate temperature. And here the ignition criterion we used was based on mass flux. So if we look at the results over time, we saw earlier, more vigorous ignition as airflow increased and with the fragmented firebrands versus the single large firebrands. This model did predict that ignition would occur with the 3 synthetic polymeric insulations, which were the 2 polystyrenes and the polyurethane. But this model does not have any parameters for melting, so that would need to be accounted for. So that's a little bit inaccurate in that case. So it might mean that flash flaming would occur around those times due to the melting. So these experiments conducted on firebrand firebrand ignition of insulation materials showed an increase in ignition likelihood with increased firebrand fragmentation and airflow rates. And we developed a simple model for ignition, and it predicted the same trends as the material ignition experiments. And then further investigation is needed into the heat transfer mechanisms, and a simpler firebrand geometry would allow for further analysis of the firebrand substrate coupling. So moving on, I also looked at the heat transfer characterization of a hot body deposited on a substrate. In these experiments, I wanted to focus purely on the heat transfer and not as much on the combustion effects. So a surrogate firebrand was used, and the insulation material that was, or the insulation substrate material that was used was calcium silicate, which is non-combustible. And in the previous experiments with the firebrand deposited on the attic insulation materials, we saw that the firebrands would sink in to the substrate over time. So we wanted to see how that would also affect the heat transfer if the firebrand was sitting on the top surface or if it was embedded. And so that's why we have an embedded configuration and embedded configuration. So if we looked at just the cooling rate curves of the embedded versus the embedded firebrands over time with different airflow conditions, which was an impinging jet, we saw that at the end of 2 minutes, the embedded was about 100 degrees higher than the bedded case for the same flow conditions. So if we look at an energy balance of the surrogate firebrand here, we can see that we have our 3 terms: radiation, convection, and conduction, but we don't know the heat transfer coefficient, and we also don't know the conductive resistance for this specific case. So these are the terms. So we used I conducted experiments with naphthalene sublimation in the same configuration to determine the heat transfer coefficients for the different airflow conditions. And then using an optimizer, we were able to find, or optimizing using the known radiative properties, the known heat transfer coefficient, and then the known cooling rate curve for a set of tests, we were able to optimize for the effective conductive resistance. And then that could be used to model further tests. So here, using this analysis on the firebrand, the energy balance, we can look at the relative contribution from conduction. And so I introduced this term eta. And if eta is 1, that essentially means there's very little cooling contribution from conduction, and then a higher value would indicate more conduction cooling. So here we can see for 2 different flow conditions presented in the bedded and embedded cases, the embedded had much higher relative contribution from conduction compared to the bedded case, which had very little conductive cooling based on this eta value. And just to look further, the bedded cases were also run with 2 different substrate materials that were also non-reacting, stainless steel and aluminum. And when there was a higher thermal effusivity material for the substrate, we did see higher relative contributions from conduction that were more on the same level as the embedded case. So we found that the surrogate firebrands maintained higher temperatures in the embedded configuration, and then in the bedded configuration, conduction contributed little to the overall cooling, and then conduction played a more significant role in the embedded firebrand cooling. And then my final work was looking at fuel bed ignition signatures. So in a lot of firebrand ignition experiments, or just ignition experiments in general, the definition of ignition is a little bit qualitative. Like, we saw flames, that means ignition occurred, but I wanted to look for a more quantitative definition of ignition, because 2 different people could look at an ignition event and say, well, oh, I only saw a brief flicker of flame, it lasted for 1 second, that's not ignition. And another person could say, yes, ignition is just if we see flames of, at least half a second. So using the same impinging jet from the previous experiments that was well characterized, and cellulose insulation material as a fuel bed, and reacting firebrands that were in the same size and shape as the surrogate firebrand, experiments were conducted looking at the ignition of cellulose material. And the firebrands were produced in the same method in a furnace to ensure that flames that were visible in the test were from the fuel bed and not the firebrand. And 2 different flow conditions were tested. So here's just kind of showing what the test looked like over time. So we can see there's clear thermal degradation within the fuel bed over time. And we can also see that the firebrand does sink into the material over time. And so there's clearly, you can see this growing smoldering area. There's something occurring in the fuel bed. So there's a growth rate of the reacting area. We had an IR camera viewing this test, and the IR camera can be used to look at firebrand temperature, but it can also be used to look at the thermal propagation within the fuel bed. So if you threshold the image at a couple different temperatures, you can kind of see like what area was above 500 C or above 800 C at a given time. And we can look at the time history of this for the course of the test to see how the thermal wave is propagating through the fuel bed. So I introduced a non-dimensional reacting area to this. So the initial reacting area, which was the initial area above 500 C versus the current area that is above 500 C. And we look at this over time. So you can see this for the 2 different flow conditions here. And this dashed line indicates where I observed flaming ignition. And we can kind of see, looking at this plot, that there are kind of straight line slopes. And whenever you see a straight line slope, you want to see what the slope is and what that growth rate is. So here this is just me eyeballing it, which isn't the best way necessarily, but we can see that on the left-hand graph, there are 3 distinct areas. So using an optimization method, looking at the times that were best for have a split and the best slopes and how many splits we would also need, I optimized for the slopes at each point to look at how the reacting area, the non-dimensional reacting area, is growing with time. And then the error cutoff was 5% for this case, for these cases. And for the lower flow condition, we generally needed 3 to have less than 5% error, but for the higher flow condition, only 2 phases were needed. So if we look at the slopes over the course of the test, we can look at the means here, and we can see that the third, or the final, I guess is a better way to put it, because in some cases there was only 2 slopes, but the final phase had much higher values of non-dimensional reacting area growth rate. And we can kind of look at this as there's a preheat phase where the non-dimensional reacting area isn't growing very much at all. And then in the case where there's 3 phases, that second phase would be smoldering ignition, and then that final phase would be flaming ignition. And as I mentioned before, we optimized for the times to the splits. And so that time to the final phase would hopefully correspond with the flaming ignition time, which would give us a more quantitative definition of ignition, which would be that transition to a higher non-dimensional reacting area growth rate. And so here at the bottom is the observed time to ignition by me as I went through the test data, and then the predicted time to ignition is from the optimization of the non-dimensional reacting area growth rate. And there was pretty good agreement between the cases. So that was my method for determining a quantitative definition of ignition in these tests. And then these 2 that are pointed out are the tests that were presented previously. So as I said, I was looking at what are the hazards associated with firebrand deposition in the WUI, and what threats do firebrands pose to structures. So from my first set of experiments, we saw that airflow condition and geometric configurations affect ignition. So we had increased airflow leading to higher firebrand temperatures and reactivity. And then from the hot body heat transfer, we saw it's very dependent on the geometric configuration. So whether or not it's bedded or embedded. And the non-dimensional reacting area growth rate provides a quantitative definition for ignition. Yeah, thank you for your time. I would love to take any questions you guys might have.
All right, yeah, thank you, Savannah. That was awesome. Really kudos for going and developing your own convective heat transfer coefficient, because that's really hard work. So good job on that. Well, and all of it. So there's a question in the chat box here. Can you talk about the contact between the firebrand or firebrands and the substrates that were not smooth, like the denim, cellulose, etc., and if that affected the repeatability of the experiments?
So I'm assuming that means obviously my first experiments. So I'm gonna go early slide. Here we go. So it would affect things, obviously. And we did see more variation in the denim and cellulose ignition times versus the polystyrenes and the polyurethane, which didn't really see ignition. We did see a lot of variation, but we attributed that to differences in the probably flame retardant loading, because the flame retardants are added to the recycled denim and the cellulose afterwards, because they're recycled, so they add flame retardants afterwards. But I would say the contact area probably has an effect, but the denim and the cellulose kind of deform as soon as the firebrand is placed on it. So it's soft, so it kind of conforms and you actually have more contact area in that case.
Gotcha. I already have a somewhat related question here. As you were talking, it sort of dawned on me that it seems like in a lot of these cases, you saw smoldering ignition before flaming. So flaming ignition was kind of a transition from smoldering. Was that true?
Yeah, definitely, especially in the last experiments that I did the more in-depth study of ignition.
Were there many that went direct to flaming, or very few?
In the cases with the higher airflow condition, yes. So this one, clearly there was smoldering before, and you would generally see the flames would be at the edge of the reacting area. But in the cases where ignition occurred quicker, it was generally closer and there was just all of a sudden flames. But in these cases, and in some cases, even there would be kind of like a little island of char that you would see out here, and that might be where ignition occurred, just based on how the thermal wave was propagating through material and how the airflow was within the cellulose, because it is porous.
Right. Oh, makes for a complicated problem for sure.
Yes, for sure.
Awesome. So if there are no other specific questions about Savannah's work, Sam had one for all three speakers. And he says you believe that you had many choices of topics for your PhD. So what brought you to studying buoy fires? Savannah, since you're up, do you want to answer that first?
Yeah, so I got into engineering because I liked science and I wanted to be able to actually help people directly with my skill set. So that's what drew me to engineering. And when I was in grad school, I honestly didn't know fire research was really a thing until I came to UT, or I was looking at UT as a possible school, and the UT Fire Research Group. And I was like, wow, that's awesome. I'd love to study that. And it's very prevalent in the news, every so often throughout the year. And it just seemed like a great way to put my engineering skills to use and actually be able to do something that maybe not what I do right this second is helping someone tomorrow, but one day it will. And it felt like a more actually real world applicable research avenue for me. That's what I thought about it.
I hear you. I like it. Nima, do you want to answer next?
Yeah, sure. So I wanted to, well, my major in civil engineering is computational mechanics. So it was about simulations, but for sure not in fire. And I always wanted to work on the risk side of the problem in urban scale. But then I honestly never thought it would be with wildfire as the hazard. So when Topsfire happened, we started reading a bit about it. And then as we went through it, we got kind of into it, and it got more and more interesting. So, and the topic is demanding, and we need to find practical and timely solutions. So that's why I stick to it. and I'm pretty happy with
Nice.
my research.
That's awesome. Jacques, I know you answered in the chat box, but do you want to quickly explain for YouTube?
Yeah, I'll just give a brief. I mean, I'm the same as the other two speakers. I come from a chemical engineering background, actually, focusing on polymer processing. And I'm actually also from South Africa, so fire protection is not actually a thing there. Moved to the US for my MS, like, oh, fire, this is actually a cool thing I could do, focused on material flammability. And when it came to the point where I was like, okay, I got to decide what I want to do for my PhD, Dr. Michael Goldner was still at Maryland, and he was very active in the firebrand research. And I'm like, well, that's maybe a topic that I can use with my knowledge in pyrolysis modeling for polymeric materials, but also my interest for a lot of research, because a lot of this stuff requires a lot of tedious research. And as Savannah also mentioned, it's in the news everywhere. And even if my models that I develop help one person in the future, it's a very noble thing to do. So that's why I got into it.
That's awesome. Well, I know we've gone over time, so I will let those of us in the US probably go eat some dinner. But thank you all three of you for fantastic talks, and I wish you the best in future endeavors, whether that's graduating or going on to postdocs, but it's awesome. So yeah, thank you guys. We've got a webinar, another student round coming up in February, so stay tuned for all the information on how to join that. And we'll see you next month. Thank you.
Thank you.
Thank you.
Thank you.